Hello everyone, I am Karina from BSc Chemistry Honors Final Year. Today's our chapter is from Physical Chemistry book of Pradeep's by Dr. S.C. Khetarpal. Photochemistry. Photochemistry is defined as the branch of chemistry which deals with the study of interaction of radiation with matter, resulting into a physical change or into a chemical reaction called photochemical reaction, whose rates and mechanisms are studied after initiation by the radiant energy. Though the term radiation includes all types of electromagnetic waves from very low frequency microwaves to medium frequency infrared, visible and ultraviolet radiation to high frequency X-rays and gamma rays. The radiation of photochemical importance are those which lie in the visible and ultraviolet region from 8000 to 2000 angstrom. Thus, the two main processes studied under photochemistry are photophysical processes, photochemical processes, or photochemical reactions. Photophysical processes are those processes which takes place in the presence of light which do not result into any chemical reaction. These processes arise on account of the absorption of light by substances followed by the emission of absorbed light. If the absorbed light is emitted instantly, the process is called fluorescence. If absorbed light is emitted after some time lag, the process is called phosphorescence. Further, if the energy of light absorbed is sufficiently high, the electrons may not only jump to the outer level but may leave the atoms completely. The process is called photoelectric effect. The photophysical processes include phenomena like fluorescence, phosphorescence, and photoelectric effect. Photochemical reactions are those reactions which takes place by absorption of light by the reacting substances. These reactions are generally brought about by the absorption of light radiations of the visible and ultraviolet region which lie between 8000 to 2000 angstrom as already mentioned above. In these cases, the light energy absorbed is stored within the substance and then used for bringing about the reaction. A large number of different type of reactions can be brought about by exposure to suitable light. For example, synthesis, decomposition, oxidation, reduction, polymerization, isomeric change, etc. Two well-known examples of photochemical reactions are given below. Combination of hydrogen and chlorine to form hydrogen chloride. Photosynthesis of carbohydrate in plant taking place in presence of chlorophyll, the green coloring matter present in the leaves. It may be pointed out that the photochemical reaction takes place when incident photon has sufficient energy so that it can result in the excitation of one of the reactant from ground electronic state to excited electronic state, as we already discussed. Difference between photochemical reactions and thermochemical reactions, or simply called thermal reactions. The main points of a difference is thermochemical reaction and photochemical reaction are summed up in table. Thermochemical reaction. These reactions involve the absorption of heat. They can take place even in the dark. Temperature has significant effect on rate of a thermochemical reaction. The free energy change of a thermochemical reaction is always negative. In these reactions, activation energy arises from the intermolecular collisions or it is supplied in the form of heat. When a reaction mixture is exposed to heat radiation, all the reactant molecules absorb these radiations and get excited almost to the same extent. That is, there is no selectivity. Photochemical reactions. These reactions involve absorption of light. The presence of light is the primary requisite for the reaction to take place. Temperature has very little effect on the rate of a photochemical reaction. Instead, the intensity of light has a marked effect on the rate of a photochemical reaction. The free energy change of photochemical reaction may not be negative. A few examples of photochemical reactions for which delta G is positive and still they are spontaneous are synthesis of carbohydrate in plants, ozonization of oxygen, decomposition of HCl into H2 and Cl2. In these reactions, activation energy is acquired by absorption of photons of suitable energy. When a reaction mixture is exposed to light radiation, the molecules of one of the reactants may get excited independent of the presence of other species. Only Br2 molecule in a mixture of H2 and Br2. In the present chapter, we shall discuss mainly the law of photochemistry, examples of some photochemical reactions, the mechanisms by which they proceed, and certain terms like fluorescence, phosphorescence, chemiluminescence, etc. Laws governing absorption of light. When a monochromatic light consisting of a single wavelength is passed through a medium, some light is absorbed by the medium and hence the intensity of the light incident light decreases. The decrease of intensity on passing through a pure homogeneous medium, pure liquid, is governed by Lambert's law, and decrease of intensity on passing through a solution is governed by Beer's law. Lambert's law. This law, put forward by Lambert in 1760, states as under. When a monochromatic light is passed through a pure homogeneous medium, the decrease in the intensity of light with thickness of the absorbing medium at any point x is proportional to the intensity of the incident light. That is the intensity of light at point x. Mathematically, minus di upon dx directly proportional to I, or minus di upon dx is equals to ki, where di is a small decrease in intensity of light on passing through a small thickness gx. I is the incident light intensity just before entering the thickness dx, and the constant of proportionality k is called the absorption coefficient depending upon the nature of the absorbing medium. The intensity I at any point x can be found in terms of original intensity I naught. It can be written as di upon I equals to minus k dx. When x equals to 0, I equals to I naught, x is equals to x, I is equals to x. On differentiating these equations, and we will found the result I equals to I naught e raised to power minus kx. This equation expresses how original intensity is reduced to intensity I after passing through a thickness x of the medium. The difference between I naught and I obviously gives the intensity of the light absorbed. Thus I absorbed is equals to I naught minus I is equals to I naught minus I naught e raised to power minus kx. Now it will be as I is equals to I naught into 10 raised to power minus k dash x. K dash is equals to k upon 2.303, called extinction coefficient of substance. Now it is this quantity which is called absorption coefficient or absorptivity of the substance. The physical significance of the extinction coefficient or absorptivity follows more clearly from the equation 6th. I is equals to 1 by 10 of I naught. Hence extinction coefficient or absorptivity may be defined as follows. The extinction coefficient or absorptivity is the reciprocal of that layer thickness expressed in centimeter at which the intensity of light falls to 1/10 of its original value. Beer's law. This is an extension of Lambert's law put forward by Beer in 1852. It is applicable to solutions and states as under. When a monochromatic light is passed through a solution, the decrease in the intensity of light with the thickness of solution is directly proportional not only to the intensity of incident light but also to the concentration of the solution. Thus, for a solution, minus di upon dx directly proportional to I into C minus di upon dx is equals to IC is a constant of proportionality and called molar absorption coefficient, which is and it is pronounced as epsilon. Its value depend upon nature of absorbing solute and the wavelength of light used. Di upon I is equals to minus EC dx. On integrating it, we will found in the last I is equals to I naught e raised to power minus epsilon Cx. This equation shows that the intensity of monochromatic light decreases exponentially from I naught to I with increase in thickness x and concentration C. The intensity of light absorbed by the solution when it passes through its length x of the solution will be given by I absorbed is equals to I naught minus I is equals to I naught minus I naught e raised to power minus epsilon Cx is equals to I naught into 1 minus e raised to power minus epsilon Cx. Now this equation on solving, I is equals to I naught into 10 raised to power minus epsilon dash Cx. Epsilon dash is equals to epsilon upon 2.303, which was earlier called molar extinction coefficient of absorbing solution. Now it is this quantity which is called molar absorption coefficient or molar absorptivity of the absorbing solution. The physical significance of molar extinction coefficient or molar absorptivity follows from equation 13, which can be written as I is equals to 1 upon 10 I naught. Hence, molar extinction coefficient or molar absorptivity may be defined as the reciprocal of that thickness of the solution layer of 1 molar concentration, which reduces the intensity of light passing through it to 1/10 of its original value. It may be pointed out that gases follow Beer's law and not Lambert's law. Units of molar absorptivity or molar absorption coefficient. It is a dimensionless quantity. In SI units, X is in meters and C is in mole per meter cube. So E dash is equals to meter cube per mole per meter. So meter square per mole. Some other terms commonly used in spectrophotometry. Spectrophotometry deals with the measurement of intensity of light absorbed when it is passed through a sample of known thickness and concentration, that is measuring the intensity of transmitted light relative to that of the incident light. It is especially useful when one substance in the reaction mixture has a strong absorption in the spectral range. In these studies, the following terms are commonly used. Transmittance. The ratio I upon I naught, that is the ratio of intensity of transmitted light from the solution to intensity of the incident light, that is the fraction of incident light transmitted, is called transmittance. Transmittance is equals to I upon I naught. Absorbance. The logarithm of reciprocal of transmittance log 1 by T or log I naught by I is called absorbance A or extinction E, formerly called optically density D. Absorption is equals to extinction is equals to optical density is equals to log 1 by T is equals to log I naught by I. Specific extinction coefficient. It is defined as the extinction or optical density or absorbance per unit length and unit concentration of the solution. Ks is equals to D upon Cx. Molar extinction coefficient. Minus log I upon I naught is equals to minus log T is equals to A or D is equals to epsilon dash Cx. If x equals to 1 centimeter, C is equals to 1 mole per liter, so epsilon dash is equals to D or A. Hence, molar extinction coefficient may be defined on the optical density or the absorbance of the solution having 1 centimeter thickness and concentration equal to 1 mole per liter. Thus, a plot of absorbance A versus concentration C will be a straight line passing through the origin with slope epsilon dash x. Limitations of BS law. The law holds good only for monochromatic radiations. This law is applicable only to dilute solutions. At higher concentration, the interionic interaction disturbs the absorption of incident radiation. The temperature should almost remain constant. Too much rise in temperature shift the absorption band towards longer wavelength, called bathochromic shift. Now some numerical problems are given on these formulas. Laws governing photochemical reactions. Law of photochemistry. There are two important laws of photochemistry as explained below. Grothus-Draper law. This law is also called first law of photochemistry. It was put forward by Grothus on theoretical ground in 1818 and confirmed by Draper by experiment in 1839. It states as under: when light falls on a body, a part of it is reflected, a part of it is transmitted, and rest of it is absorbed. It is only the absorbed light which is effective in bringing about a chemical reaction. The above law, however, does not imply that the absorbed light must always result into chemical reaction. The absorbed light may simply bring about phenomena such as fluorescence, phosphorescence, etc. Similarly, the absorbed light energy may be simply converted into thermal energy. Example, in case of potassium permanganate solution, the light energy is absorbed strongly but no chemical shift effect is produced. Further, in some cases, it is observed that light energy may not be absorbed by reacting substance directly, but may be absorbed by some other substance present along with the reacting substance. The energy thus absorbed is then passed on the reacting substance which then starts reacting. The process is called photosensitization and has been discussed in this section in detail. 4.11. A well-known example is that of photosynthesis of carbohydrate in plants where chlorophyll acts as a photosensitizer. The expression for light absorbed when it passes through a pure liquid or through a solution already been derived in section 4.3, equation 4 and 11. Number 2. Stark-Einstein law of a photochemical equivalence. This law is also called second law of photochemistry. It was put forward by Einstein in 1905 and Stark 1908. It states as under: every substance or molecule that take part in chemical reaction absorbs one quantum of radiation to which the substance is exposed. If mu is the frequency of absorbed radiation, then the energy absorbed by each reacting atom or molecule is one quantum. that is h mu, where h is Planck constant. The energy absorbed by 1 mole of reacting molecules will then be given by E is equals to n h mu. N is the Avogadro number. Mu is equals to c upon lambda, so E is equals to nhc upon lambda. C is velocity of light, L lambda is equals to wavelength of absorbed radiation. The energy possessed by 1 mole of photons or the energy absorbed by 1 mole of reacting molecules is called 1 Einstein. Now some numerical problems are given. Problems for practice. Interpretation of the Einstein's law. If Einstein's law is correct, every reacting molecule will absorb 1 quantum of radiation. Hence, the number of reacting molecules should be equal to the number of quanta absorbed. However, it is found that in a number of cases, a small amount of light absorbed can bring about a large amount of reaction, whereas in some other cases, large amount of light absorbed can bring about only a small amount of reaction. This was explained on the basis that all the molecules present do not absorb the radiation. Firstly, only a few molecules absorb the radiation. These molecules are said to have been activated. These activated molecules then react with the other molecules and thus bring about a large amount of chemical reaction. On the other hand, in certain cases, the activated molecules get deactivated and no further reaction takes place. The first stage is called the primary process. These reactions involved in the second stage are called secondary processes. To relate the number of quanta absorbed with the number of reacting molecules, a term called quanta efficiency or quantum yield has been introduced. It is expressed as quantum yield is equals to number of molecules reacted in a given time divided by number of quanta of light absorbed in the same time, or number of molecules reacting in a given time divided by number of Einstein of light absorbed in the same time. Hence, quantum efficiency may be defined as the number of moles reacting per Einstein of the light absorbed. If Stark-Einstein law is strictly obeyed in the form already stated, quantum yield phi should be equal to unity. However, studies have shown that the law is applicable only to the primary processes. Hence, it is sometimes preferred to it as follows. Each molecule that gets activated to initiate the reaction absorbs 1 quantum of light. Experimental determination of quantum yield of a photochemical reaction. Theory of process. For experimental purpose, the expression for quantum yield may be written as phi is equals to rate of chemical reaction divided by quanta absorbed per second. Thus, to determine the quantum yield of any photochemical reaction, we have to measure the rate of chemical reaction in terms of molecules per second, the quanta absorbed per second. Apparatus. The apparatus used for measuring the above two quantities is shown in figure. It consists of following part from left to right. A source of radiation emitting radiation of suitable intensity in the desired spectral range. The commonly used sources are filament lamps, carbon metal arcs, and various gas discharge tubes. Lens of suitable focal length. Monochromator or filter which cuts off the all radiations except the radiation of the desired wavelength. Slit to get a fine beam. A cell placed in thermostat and containing the reaction mixture. The cell is made of glass or quartz and has optically plain windows for the entrance and exit of light. Glass is only used only if the wavelength of light used lies in the visible region. For radiation with wavelength below 3500 angstrom, the cell completely made of quartz is used. Recorder. It is usually a thermopile or an actinomer which is used to measure intensity of the radiation. The principle of a thermopile and that of an actinomer are briefly explained below. A thermopile is a set of thermocouples, rods of two different metals, for example, silver and bismuth, are joined alternatively. If only two rods are connected, it constitutes a thermocouple. One set of junction is soldered to metal strip blackened with platinum or lamp black, and the other set of junction is protected completely from radiation by placing the system in a box. The radiations falling on the blackened metal strip are almost completely absorbed by it. As a result, this set of junction become hot. The temperature difference of hot end and a cold end produces a current which can be measured by connecting a milliammeter to the thermopile. By calibrating the thermopile with radiation of known intensity, the intensity of desired radiations can be measured. A chemical actinomer is a device in which gas mixture of solutions sensitive to light are used. The working of this device is based upon the fact that a definite amount of the radiation absorbed brings about a definite amount of chemical reaction. The most commonly employed is the uranyl oxalate actinomer, which consists of 0.05 molar oxalic acid and 0.01 molar uranyl sulfate UO2SO4 solution in water. When exposed to light, the following reaction takes place. Uranyl sulfate acts as photosensitizer. The extent of reaction is measured by titrating the oxalic acid solution with potassium permanganate solution. The actinomer is first calibrated against a thermopile. This actinomer can be used for measuring only the intensity of radiation lying in the range 2000 to 5000 angstrom. Procedure: measurement of intensity of light absorbed. First, the empty cell or the cell filled with solvent alone, in case of solution, is placed in thermostat. The monochromatic radiation is allowed to pass through the cell for a definite time. The reading is taken on the recorder. From this we get energy of incident radiation. Now reactants are taken in cell and radiations are allowed to pass through it for definite time, and the reading is taken again. The difference between the two readings gives the total energy absorbed by reactant in a given time. Thus from this the intensity of radiation absorbed is calculated. I absorbed is equals to total energy absorbed divided by volume of reaction mixture into time in second. Measurement of rate of reaction. The rate of reaction can be studied as usual. For this purpose, either the change in some physical properties followed or samples of the reaction mixture are removed periodically from the cell and analyzed. Knowing the rate of reaction and the intensity of light absorbed, the quantum yield of the reaction can be calculated. Now numericals are given. Problems of practice. Some example of photochemical reactions. Based upon quantum yield, the various photochemical reactions have been divided into three categories. It is obvious that quantum yield of photochemical reactions vary within very wide limits from 0.01 for the photosynthesis of HBr to 10 raised to power 6 for the combination of hydrogen and chlorine. The reason for very high or very low quantum yield has already been discussed, wherein it was stated that a photochemical reaction takes place in two steps, which are primary process. This involves activation of certain molecule by absorption of light, or dissociation of certain molecule to produce active atoms or free radical. Secondary process. These involve the reaction of activated molecules or the product of the primary process with the other molecules, or the deactivation of activated molecules. Now some example of photochemical reactions are given in this table. Photolysis. Photochemical decomposition of hydrogen iodide. The photolysis of Hi to give H2 and I2 has been studied in wavelength range 2070 to 2820 angstrom, and the quantum yield of this reaction has been found to be approximately 2. This has been explained by proposing the following mechanism for photolysis of Hi. Secondary process is the product of primary process, then take part in the secondary process as follows. All the secondary processes are not important. The reaction third and fifth are highly exothermic, and that the heat produced result into the dissociation of products of these reactions. Reaction second is endothermic and hence takes place slowly. Thus the only secondary process of importance are reaction first and fourth. Rewriting these reactions of primary process and two important reactions first and fourth of secondary process, we have. Adding these equations, we find no distinction between the excited iodine atom and the normal iodine atom. We get overall reaction 2Hi plus H mu to form 2H2 plus I2. Number 2 is photosynthesis of HBr. Now this reaction will take place H2 plus Br2 to form 2HBr. The quantum efficiency of this reaction is very low, about 0.01 at ordinary temperature. This is explained by proposing the following mechanism for above reaction. Primary process Br2 plus H mu to form 2Br, and the secondary process is the hydrogen atom in reaction first attacks Br2 according to reaction second, producing HBr and Br atom. The Br atom thus produced attacks more of H2 according to reaction first, producing H atom again. As a result, reaction first and second should repeat over and again. Reaction first is endothermic, reaction second and third depend upon formation of H atom in reaction first is endothermic and hence takes place slowly or almost does not tend to take place. Reaction second and third are very slow. Secondary process is the fourth reversal of the primary process. Thus the Br atom formed in the primary process do not combine to form HBr. Instead they combine together to give back Br2. As a result, the quantum yield of reaction is very low at ordinary temperature. Now the quantum yield of above reaction increases with increase of temperature. This is obviously because of the fact that the reaction first, which is endothermic and requires high energy of activation, become faster at high temperature because the required energy of activation become available at higher temperature in the form of heat. Photosynthesis of HCl from H2 and Cl2. This is an example of a reaction whose quantum yield is very high, 10 raised to power 4 to 10 raised to power 6. This reaction may be represented as H2 plus Cl2 to form HCl. Luminescence. When a solid body, a piece of iron, is heated, it first becomes red hot and then becomes white hot. and hence it begins to glow. The glow can be produced by methods other than the action of heat. When the excited electron jumps back to the inner level, light is emitted. The light thus produced is called cold light. The glow produced in a body by methods other than the action of heat, that is the production of cold light, is called luminescence. The body emitting the cold light is called luminescent. Luminescence may be any one of the following three types. Chemiluminescence. When a photochemical reaction takes place, light is absorbed. However, there are certain reactions taking place at ordinary temperatures in which light is produced. The emission of light in certain chemical reactions at ordinary temperature is called chemiluminescence. Thus, chemiluminescence is just the reverse of a photochemical reaction. A few examples of chemiluminescence are as under. The light emitted by glowworms, fireflies, is due to oxidation of protein luciferin present in the glowworms by atmospheric oxygen in the presence of enzyme luciferase. The oxidation of yellow phosphorus in oxygen or air to give P2O5 at ordinary temperature is accompanied by the emission of visible greenish-white luminescence. Oxidation of decaying wood containing certain forms of bacteria also produces luminescence. In all the above cases, a part of whole of the energy emitted during the reaction, instead of appearing as heat, is used up for the excitation of electron, which when jump back to the inner orbit, resulting into the emission of light. Fluorescence. There are certain substances which when exposed to light or certain other radiations absorb the energy and then immediately or instantaneously start re-emitting the energy. Such substances are called fluorescent substances and the phenomenon is called fluorescence. Obviously, the absorption of light results in the excitation of electrons present in the atoms or molecules of this substance, followed immediately by the jumping back of excited electrons to the lower levels. As a result, the absorbed light is emitted back. The word instantaneous used above implies that the time between absorption of energy and remission of absorbed energy is not more than 10 raised to power minus 8 seconds. Thus, fluorescence starts as soon as the substance is exposed to light and the fluorescence stops as soon as the light is cut off. A few examples of substances showing the phenomena of fluorescence are fluoride CaF2, certain organic dyes such as eosine, fluorescein, etc. Vapor of sodium, mercury, iodine, etc. Certain inorganic compounds such as uranyl sulfate. It is interesting to observe that in the phenomena of fluorescence, the wavelength of emitted light is usually greater than that of the absorbed light. This is explained on the basis that the energy absorbed raises the electron to a sufficiently high level, but the return of excited electron to the original level takes place in step. Through the intermediate level, the energy thus produced in every jump is smaller and hence wavelength of light emitted is larger than that of the absorbed light. In case of mercury vapor, the emitted light has the same wavelength as that of the absorbed light. This phenomenon is called resonance fluorescence. In certain cases, light of shorter wavelength is emitted. This is explained by suggesting that the emitted light contains the absorbed energy as well as some energy present in the system before absorption. Phosphorescence. In case of fluorescent materials, the fluorescence stops as soon as the external light is cut off. However, there are certain substances which continue to glow for some time even after the external light is cut off. Such substances are called phosphorescent substances, and the phenomena is called phosphorescence. Thus, in a way, phosphorescence is a slow fluorescence. It is found mostly in solid, as might be expected, because in liquid the molecules have least freedom of motion. The excited electrons thus keep on jumping back slowly for quite some time. The best example of substances exhibiting phosphorescences include zinc sulfide and sulfates of alkaline earth metals. Usually a trace of heavy metal is added in the form of its sulfide, which intensifies the light emitted by the phosphorescent substances. Further, it has been found that the fluorescent substances becomes phosphorescent if fixed by suitable methods, by fusion with other substances, etc. For example, many dyes which show fluorescence when dissolved in fused boric acid or glycerol and then cooled to get rigid mass become phosphorescent. Fluorescence and phosphorescence in terms of excitation of electron, Jablonski diagram. When energy in the form of light radiation falls on certain molecules, some of the electrons present in them absorb energy and jump to the outer orbitals. The molecules are then said to be in the excited state. Most of the excited species have very short lifetime, usually less than 10 raised to power minus 6 seconds. They may either undergo a chemical change or return to the ground state. The excitation of electron occurs so rapidly that it is believed that there is not enough time for the orientation of spin of electron to change. The one which was clockwise remains clockwise, and other which is anti-clockwise remains anti-clockwise. After the excitation, thus in terms of electron spin, we can represent the excitation as follows. These states are usually expressed in terms of a quantity called spin multiplicity, which is equal to which is equal to 2s plus 1, where s is total electron spin. For a molecule containing all paired electron, s equals to 0, so its spin multiplicity is equals to 1. The molecule is said to be in singlet ground state. After absorbing photon, when the molecule is in the excited state with opposite spins, s is equals to 1 by 2 minus 1 by 2 equals to 0, so that spin multiplicity is equal to 1. The molecule is then said to be singlet excited state. When in the excited state, the electrons are present in different orbitals but with spin in the same direction, s is equals to 1, and spin multiplicity is equals to 2s plus 1 is equals to 3. The molecule is then said to be triplet state. In triplet state, excited state. Depending upon energy absorbed, the electrons may jump to any of the higher excited state, and we have a number of singlet excited state called first, second, third singlet excited state represented by S1, S2 and S3 etc. The singlet around ground state is represented by S0. The corresponding triplet excited state called first, second, third triplet excited state and represented as T1, T2 and T3. Any singlet excited state are found to have higher energy than the corresponding triplet state, and so on. The excited species can return to ground state by losing all of its excess energy by any one of the following paths. In all these paths, however, the first step is transition from higher excited singlet state to lowest excited singlet state S1. This is called internal conversion. The energy is lost only in the form of heat due to the collision with other molecules, and it does not result into the emission of any radiation. It is therefore called non-radioactive and radiationless transition. It is a very fast process and occurs in less than about 10 raised to power minus 11 seconds. Now, from the first excited singlet state, the molecule return to the ground state by any one of the following path. Path first. The molecule may lose rest of the energy also in the form of heat, so that complete path is non-radiative. Path 2. The molecule may release the energy in the form of light or ultraviolet radiation returning to the ground state from the first excited singlet state. Hence, it is a radioactive transition. This is called fluorescence. It occurs for about 10 raised to power minus 8 seconds after absorption, so that a substance fluorescence is only the presence of absorbed radiation. Path 3. Some energy may first be lost in transition from first excited singlet to first excited triplet state between state of different multiplicity, that is S1 to S2, or similarly S2 to S2, T2, S3 to T3, or S1 to T1 in the form of heat, so that it is again a radiation-less transition. It is also called intersystem crossing ISC. Such transitions are normally forbidden, but whenever they occur, their rate is very slow. In further transition from first excited triplet state to ground state, the rest of energy may again be lost in the form of heat due to molecular collisions. Thus, the complete path is non-radiative. Path 4. After intersystem crossing, the molecule may lose the rest of the energy in the form of light in going from excited triplet state to ground state. This is called phosphorescence, as triplet state have much longer lifetimes than singlet states, such as long as an hour. Phosphorescence persists even after the removal of absorbed radiation. This may also be attributed to the fact that the transition from excited triplet state to ground singlet state are forbidden. Note that fluorescence involves a radiative transition between two states of same multiplicity, whereas phosphorescence arises due to radiative transition between two states of different multiplicity. Fluorescence usually to singlet, and phosphorescence usually from triplet to singlet. It may be observed that the energy emitted during fluorescence as well as the phosphorescence is less than the energy absorbed during excitation, as a part of energy is dissipated as heat in the internal conversion and intersystem crossing. Hence, the frequencies emitted during the fluorescence and phosphorescence are smaller, or wavelengths are longer than those of the light absorbed for excitation. Further, the energy is lost not only as heat but also in undergoing a chemical reaction. As singlet excited states return quickly to the ground state, there is no chance for a chemical reaction. However, if the molecules are in the triplet excited state, they return to the ground state slowly and thus get sufficient time to undergo a chemical reaction. Thus, molecules undergoing chemical reactions are those which are first in the excited triplet state. The paths followed as explained above may be compared with a two-floor building having steps, ramps and windows. First step of fall path is like a ball falling from second floor to the first floor by bouncing on steps going from second floor to first floor. If the ball now falls on the ramp going from first floor to the ground floor, it is like path first. If ball after coming to first floor falls out of the window, it is like path second. If after coming to first floor the ball moves on some steps and then falls on the ramp going from first floor to ground floor, it is like path 3. If the ball after having come to the first floor moves on some steps going from first floor to ground floor and then jumps out of the window, it is like path 4. Quenching of fluorescence, Stern-Volmer equation. As already explained, the fluorescence occurs when certain molecules absorb energy, that is, they are activated and then immediately re-emit energy. If the excited molecules are deactivated and the fluorescence stops, the phenomenon is called quenching. The substances which are responsible for stopping of fluorescence called quencher, usually represented by the symbol Q. Quenching may occur in either of the following two ways. When activated molecule undergo a change from singlet excited state to triplet excited state, this is called internal quenching. When the activated molecules collide with other molecules, quenchers, which are externally added species and transfer their energy to those molecules, this is called external quenching. Thus, the various steps from activation to deactivation may be represented. A plus H mu to form A star activation. A star to form rate constant K1, A plus H mu fluorescence. A star with rate constant K2 to form internal quenching A. A star plus Q quencher in the rate constant K3, A plus Q dash external quenching. Applying steady state principle to concentration of A star and keeping in mind that the rate of reaction is directly proportional to intensity of light absorbed, we have IA is equals to K1 A star plus K2 A star plus K3 A star Q. IA represent intensity of light absorbed. IF represent intensity of fluorescence. Then the quantum yield of fluorescence in presence of quencher will be given by phi f or phi q is equals to if upon ia k1 a star divided by k1 a star plus k2 a star plus k3 a star q is equals to k1 by k1 plus k2 plus k3 q. In the absence of quencher, when q equals to 0, the quantum yield will become phi naught phi 0 is equals to k1 upon k1 plus k2. The ratio of two quantum yield will be phi naught phi 0 upon phi q is equals to k1 plus k2 plus k3 q divided by k1 plus k2 is equals to 1 plus k3 q by k1 plus k2. Putting 1 upon k2 plus k1 plus k2 is equals to called the lifetime OA star in the absence of quencher. Phi naught upon phi q is equals to 1 plus k3 torque q is equals to 1 plus ksvq. This equation is known as Stern-Volmer equation and the constant ksv is called Stern-Volmer constant. This equation shows that phi naught upon phi q varies linearly with q. The slope of line will be ksv, that is K3 torque, from which value of torque can be obtained. Photosensitization. There are many substances which do not react directly when exposed to light. However, if another substance is added, the photochemical reaction starts. The substance thus added itself does not undergo any chemical change. It merely absorbs the light energy and then passes it on to the one of the reactant. Such a substance which when added to a reaction mixture helps to start the photochemical reaction but itself does not undergo any chemical change is called photosensitizer, and the process is called photosensitization. Thus, a photosensitizer simply acts as a carrier of energy. At first instance, it appears that a photosensitizer is similar to a catalyst. However, this is not so as they act by different mechanisms. Examples of photosensitized reaction. A few well-known examples of photosensitized reaction are briefly described below. Dissociation of hydrogen molecule in presence of mercury vapor. Hydrogen molecule do not dissociate when exposed to ultraviolet light. However, when hydrogen gas is mixed with mercury vapor and then exposed to ultraviolet light, hydrogen molecule dissociate to give hydrogen atoms through the following reactions. Hg plus H mu to form Hg star plus H2 to form Hg plus 2H, where Hg star represent activation mercury atom. Thus, in the above reaction, mercury acts as a photosensitizer. The H atom being highly reactive and can easily reduce the metallic oxide, nitrous oxide, carbon monoxide, etc. In a similar manner, the dissociation of NH3, PH3, ASH3 and a number of organic compounds is photosensitized by mercury. Certain combination reactions are given, for example, 2H2 plus O2 to form 2H2O, N2 plus 3H2 to form 2NH3, 3O2 plus 3O2 to form 2O3, etc. are also mercury photosensitized. Two well-known mercury photosynthesis reaction involving dissociation of H2 molecule into H atom are briefly explained below. Combination between CO and H2 to form formaldehyde and glyoxal. It is believed to take place through the following steps. And combination between H2 and O2 to form H2O and H2O2. It is believed to take place through the following steps. H2O2 may be isolated as such or it decomposes to give H2 and O2. However, under certain condition, the amount of H2O2 predominates. Cadmium vapor also have been used as a photosensitizer in number of reactions such as polymerization of ethylene, decomposition of ethane, propane, etc. into H2 and lower hydrocarbon, etc. Dissociation ethylene. When a mixture of ethylene and mercury vapor is irradiated with light of wavelength to 53.7 nanometer, the following reaction are supposed to occur. Decomposition of ozone in presence of fluorine as photosensitizer. Ultraviolet radiations are absorbed by Cl2 molecules and dissociate them into Cl atom, but they have very little effect on the decomposition of ozone. However, if the mixture of ozone and chlorine is exposed to these radiations, chlorine will act as a photosensitizer in the decomposition of ozone and is unchanged at the end of the reaction. The reaction starts by absorption of radiation of wavelength 4785 angstrom by Cl2 molecules, resulting in the dissociation into Cl atoms, followed by the reactions. Decomposition of diazomethane, isomerization of butene from cis to trans in presence of SO2 as sensitizer, decomposition of oxalic acid in presence of uranyl sulfate, photosynthesis of carbohydrates in plants. Photoinhibitors. It has been found that the presence of certain substances considerably reduces the quantum yield of some photochemical reactions. For example, as already discussed in the photosynthesis of HCl, the presence of traces of oxygen reduces the quantum yield of this reaction. Substances like nitric oxide, sulfur dioxide, propylene, etc. also show similar effect. Such substances which reduce the quantum yield of photochemical reaction are called photoinhibitors. It is believed that such substances react with the chain propagating atom or radicals, resulting into the chain termination. The chain termination in the photosynthesis of HCl by the presence of traces of oxygen has already been discussed in section 4.7. Photochemical equilibrium or photostationary state. Suppose a substance A changes into a substance B by the absorption of light. That is, the reaction A to B is a photochemical reaction. If the reverse reaction can also occur either as photochemical reaction or a thermal reaction, dark reaction, the situation may be represented as A is in equilibrium B or A is in equilibrium light or thermal B. In either case, a stage may reach when the rate of forward reaction may become equal to the rate of backward reaction. Now, the absorption of light produces no further chemical change. The reaction is then said to have attained a photochemical equilibrium or a photostationary state. Example: photochemical decomposition of nitrogen dioxide. 2NO2 is in equilibrium light thermal 2NO plus O2. Dimerization of anthracene 2C14H10 is in equilibrium C28H20. Photochemical decomposition of sulfur trioxide 2SO3 is in equilibrium 2SO2 plus O2. Equilibrium constant. The equilibrium constant of a photochemical equilibrium is different from that of the ordinary chemical equilibrium. This is obviously due to the fact that the rate of a photochemical reaction doesn't depend upon the concentration of reactant, but it depends upon the intensity of the light absorbed. Thus, for the reaction A is in equilibrium with B, rate of forward reaction is directly proportional to I absorbed is equals to K1 I absorbed. Rate of backward reaction directly proportional to B is equals to K to B. When reaction is in equilibrium, rate of forward reaction equals to rate of backward reaction. K1 I absorbed is equals to K to B, or K2 by K1 equals to I absorbed by B, or K is equals to I absorbed by B, where K is equals to K2 by K1 is the photochemical equilibrium constant. From the above equation, it is clear that photochemical equilibrium constant depend upon the intensity of light absorbed. Further, the above equation may be written as B is equals to K1 upon K2 I absorbed. It follows that the concentration of products formed at equilibrium is directly proportional to the intensity of the light absorbed. Thank you.